everyone, myself Dr. P. Vijayakumar, Associate Professor, Department of ECE, Aditya University. In this session, we are going to see the noise parameters. So, different noise parameters we will be using for analyzing the noise. So, we will see some of one or two parameters in this session like noise equivalent bandwidth, noise temperature. So, at the end of this session, you will be learning the learning outcome 1, understanding the effective noise temperature, and another learning outcome is understanding the equivalent noise bandwidth. So, in the earlier session, we have seen what is meant by noise. Noise is nothing but an unwanted signal which is going to interrupt the message signal, and it is going to corrupt the message signal, thereby at the receiver the signal will be lost. So, to analyze the noise, we will be using different parameters. One of the important parameter we will be seeing here is effective noise temperature. So, effective noise temperature is a measure that represents the combined noise contribution of a system or a device as an equivalent temperature. It tells us how much thermal noise a device like an amplifier, device can be an amplifier, device can be a receiver, device can be an antenna. So, how much thermal noise a device will generate. So, if all noise were coming from a resistor at the temperature T. So, every electronic device in general adds some noise to the signal. So, when it is processing. So, instead of expressing noise as a voltage or power, we can express in terms of temperature also. So, there is a relationship between thermal noise power and temperature. So, thermal noise power is Pn and temperature is T, K is the Boltzmann constant, B is the bandwidth. So, thermal noise power is directly proportional to the temperature. So, effective noise temperature, thermal noise power is directly proportional to the effective noise temperature. If a device adds noise equivalent to a resistor at a temperature T, it is effective noise temperature. So, any device which is contributing some amount of noise at a temperature T to a resistor, that temperature is nothing but effective noise temperature. Okay. So, noise power is directly related to effective noise temperature. Okay. Generally, for a single device, how do we measure the effective noise temperature and what is the mathematical relation we follow for expressing the relation? So, effective noise temperature is denoted by a symbol TE and the noise factor is F. So, we will study what is meant by noise figure and noise factor in the next sessions. So, noise factor, for a while you assume noise factor is, let us say, F, and it is mathematically generally defined as input signal to noise ratio to the output signal to noise ratio. SNR at the input divided by SNR at the output. For a while you remember what is meant by noise figure, general mathematical formula. We will see in detail about the noise figure and different types of noise figures in the noise parameters. So, noise figure is input signal to noise ratio to the output signal to noise ratio, and T naught is the standard reference temperature 290 degree Kelvin. Effective noise temperature TE is equal to F minus 1 into T naught. F is the noise figure and T naught is the standard reference temperature. So, TE is the temperature measured at a device at temperature T. So, that is nothing but effective noise temperature. Next, so when there are many cases where the electronic systems we use a cascading connection. So, cascading connection means input side will be connected to output, output will act as input to the next device, output of second device acts as input to third device, like that. This is nothing but cascading connection. So, in general, in electronic appliances, to improve the gain, generally the devices are connected in cascade connection. So, when multiple stages like amplifiers are connected in cascade, the overall noise temperature, generally we are much interested in gain. So, gain, overall gain, generally when they are cascaded, overall gain will be G1, G2, G3. So, gain will multiply by itself, G1, G2, G3. G is equal to G1, G2, G3. But we are talking about here noise temperature. So, each device, this is one device, this is another device, this is third device, 1, 2, 3. And each device is contributing effective noise temperature. First device is contributing TE1, second one TE2, third one TE3. TE is the overall system effective noise temperature. So, the formula for computing the overall system noise temperature TE is T1 plus T2 by G1 plus T3 by G1 G2, where T1, T2, T3 are the effective noise temperatures at each stages, and G1, G2, G3 are power gains at each stages. Okay. Next, the interpretation is whenever there is a low noise, effective noise temperature, the system is acting as a best device. The noise performance is better. So, when T is equal to 0 degree Kelvin, it is nothing but a perfectly noiseless device, which is not possible. Theoretically, it is possible. Practically, always there exists some ambient temperature and external temperature. If you add both temperatures, always there will be some temperature. It will be never equal to 0 degree Kelvin. So, for a perfectly noiseless device, the effective noise temperature is 0 degree Kelvin. And this is used to compare the design of low noise amplifiers, receivers in communication and radar systems. This concept is useful in design of low noise amplifiers, receivers in communication and radar systems. So, there are many applications where we use the concept of this noise temperature, receiver sensitive analysis, design of low noise front end in satellite and microwave communication system, and also when you are characterizing the noise power in terms of temperature, we will be using this effective noise temperature. Generally, we follow power. Sometimes we use temperature as the major parameter for noise analysis. There we use the concept of effective noise temperature. All are interrelated. Everyone can be related. Power is directly related to temperature. Let us see one problem, how to solve or how to get the effective noise temperature. Assume the noise figure is given as 3 dB. So, decibels. Power gain in decibels is mathematically equal to 10 log 10, F is equal to 3. From this, F is equal to 3 by 10, 10 power 3 by 10, 10 power 0.3, which is mathematically equal to 2. That means noise figure in normal value is 2 when it is 3 dB, and effective noise temperature T, we know the formula, F minus 1 into T naught. F is 2 minus 1. T naught is a fixed value 290. So, 2 minus 1 into 290 is 290 degree Kelvin. This is the receiver effective noise temperature. And let us see how to calculate the power also. What is the noise power in watts and decibel milli? If the temperature is 290 degree Kelvin, bandwidth is 1 megahertz. Already we have seen that noise power is equal to kTB. T is given, B is given, K we know Boltzmann constant. Substituting 1.38 into 10 power minus 23, T is 290 degree Kelvin, 10 power 6 is the bandwidth. So, the overall answer is 4 into 10 power minus 15 watts. If power has to be expressed in decibel milli, what we will do is we will divide with a 10 power minus 3 and then we will apply. So, the power in decibel milli is minus 113.98 dBm. Okay. Next one, F has to be calculated indirectly because signal to noise ratio at the input and signal to noise ratio at the output is given. So, F is equal to SNR at the input by SNR at the output. So, these values are given in decibels. So, we need to convert into normal values. The normal value SNR input is 1000, SNR output is 100. F will be SNR input by SNR output, F will be 10. So, noise figure in decibels will be 10 log 10, it is 10 dB. So, TE is equal to F minus 1 into 290. F is 10 normal value, 9 into 290, 2610 degree Kelvin. This is the effective noise temperature. And next parameter is noise equivalent bandwidth, which is very important parameter. It is an important concept particularly in signal processing and communication systems. So, we will define this noise equivalent bandwidth as it quantifies the how much noise power through a filter when compared with a ideal rectangular filter. How much noise power is passing through a filter when compared with the ideal rectangular filter. And mathematically it is given as integration 0 to infinity h of f whole square df by absolute value of h of f naught whole square, where h of f is the magnitude response of the filter. This is for ideal case, this is the filter. So, the interpretation is Bn represent the bandwidth of ideal rectangular filter that would pass the same total noise power as the actual non-ideal filter passes. So real filters do not have perfect rectangular frequency responses. So the noise equivalent bandwidth provides a practical way for comparing the filters based on noise passing characteristics. The key points are noise equivalent bandwidth is slightly greater than the 3 dB bandwidth. General bandwidth, when you compare, it will be more, and it is used to determine the output noise power from the input noise power spectral density. So the output noise power is equal to noise power spectral density into bandwidth. Bandwidth into noise power spectral density is noise power. Watts per hertz into hertz. You will get watts. So one example problem, already mentioned that general 3 dB bandwidth is 1 kilohertz. Noise equivalent bandwidth is 1.11 kilohertz. Generally, NEB, noise equivalent bandwidth, is greater than general bandwidth. The filter passes the same noise power as an ideal 1.1 kilohertz rectangular filter. The application is noise equivalent bandwidth concept is used in noise performance evaluation in communication receiver, spectrum analyzers and radiometers measurement devices. So let us see one problem, how to compute the noise bandwidth for a low pass filter. We know what is meant by low pass filter. So this is a circuit of the low pass filter. If you compute the transfer function V naught of omega by Vi of omega, you will get 1 by 1 plus j omega RC. This is nothing but magnitude h of omega or gain. So absolute value of gain means absolute value of magnitude 1 by root of 1 plus omega square r square c square. So we are substituting and integrating over the limit. So what we will get? So integration of 0 to infinity h of omega whole square d omega is pi by 2 RC. The noise equivalent bandwidth is pi by 2 RC. Okay. So in this session, what we have seen, we have defined two noise parameters, effective noise temperature and noise equivalent bandwidth. These two are important parameters for analyzing the noise, and also we have seen few problems how to compute the effective noise temperature and effective noise equivalent bandwidth. So in the next session, we will be seeing some more noise parameters which will be helpful in analyzing the noise. Thank you.